Good day, everyone. I'm Vima Kate Deroilo, and for today, we will be talking about the infallibility and certainty in mathematics. Mathematics has long been revered for its perceived infallibility and certainty. This presentation delves into the philosophical underpinnings of these concepts, exploring how mathematicians and philosophers have grappled with the nature of mathematical truth. We will examine various perspectives from the empirical argument of John Stuart Mill to analytic view of David Hume and the synthetic a prior reasoning of Immanuel Kant. By investigating these viewpoints, we aim to shed light on the ongoing debate surrounding the foundation of mathematical knowledge.
Infallibility is the quality of being unable to make a mistake, fail, or be wrong. Cornerstone, the prime basis. Mathematical infallibility begins with a rigorous process of proving theorems. This involves building upon established axioms and employing logical deductions to reach irrefutable conclusions. The Pythagorean theorem has been proven using various methods over millennia, and despite the changing context in which it is applied, the theorem remains true.
How do we know that the theorem is true for every right triangle on a flat surface, not just the ones these mathematicians and surveyors knew about? Because we can prove it. Proofs use existing mathematical rules and logic to demonstrate that a theorem must hold true all the time. One classic proof, often attributed to Pythagoras himself, uses a strategy called proof by rearrangement. Take four identical right triangles with side lengths A and B and hypotenuse length C. Arrange them so that their hypotenuses form a tilted square. The area of that square is C squared. Now rearrange the triangles into two rectangles, leaving smaller squares on either side. The areas of those squares are A squared and B squared. Here's the key. The total area of the figure didn't change, and the areas of the triangles didn't change. So the empty space in one, C squared, must be equal to the empty space in the other, A squared plus B squared. Another proof comes from a fellow Greek mathematician, Euclid, and was also stumbled upon almost 2,000 years later by 12-year-old Einstein. This proof divides one right triangle into two others and uses the principle that if the corresponding angles of two triangles are the same, the ratio of their sides is the same too. So for these three similar triangles, you can write these expressions for their sides. Next, rearrange the terms. And finally, add the two equations together and simplify to get AB squared plus AC squared equals BC squared, or A squared plus B squared equals C squared. Here's one that uses tessellation, a repeating geometric pattern, for a more visual proof. Can you see how it works? Pause the video if you'd like some time to think about it. Here's the answer. The dark gray square is A squared, and the light gray one is B squared. The one outlined in blue is C squared. Each blue outlined square contains the pieces of exactly one dark and one light gray square, proving the Pythagorean theorem again. And if you'd really like to convince yourself, you could build a turntable with three square boxes of equal depth connected to each other around a right triangle. If you fill the largest square with water and spin the turntable, the water from the large square will perfectly fill the two smaller ones. The Pythagorean theorem has more than 350 proofs, and counting, ranging from brilliant to obscure. Can you add your own to the mix?
Logical certainty. Mathematics relies on deductive reasoning, where conclusions follow logically from premises. This leads to a high level of certainty. For example, in Euclidean geometry, if the axioms hold, the conclusions drawn are certain. The acceptance of basic axioms leads to the certainty of all derived theorems within that system, illustrating the power of axiomatic foundations. The The certainty in mathematics is rooted in its axiomatic systems. Once axioms are accepted, all theorems derived from them as regarded as certain within that system. Example, in set theory or number theory. Axioms such as those in Peano's axioms for natural numbers provide the foundational rules from which all further mathematical statements about numbers are derived.
TOK, we often ask, how certain can we be about this knowledge, or when can we be certain about that knowledge? But certainty on its own is not a very useful concept for evaluating knowledge. Certainty is a state of mind rather than an objective measure of knowledge. It is based on how convinced we are of the validity or accuracy of knowledge, rather than its actual validity or accuracy. The problem is that we can be very certain, but also wrong at the same time. In TOK, we can usefully distinguish between rational and irrational certainty. Rational certainty is when our confidence is justified, relying on reasoning based on evidence. Irrational certainty based on intuition or faith is not necessarily wrong, but it is harder to change if it is wrong. If a person is certain based on evidence, you can change their mind by providing new or better evidence. But if they are irrationally certain, evidence won't necessarily make a difference to them. It is often hard to tell the difference, however, because it often seems like our irrational beliefs are supported by evidence. But this evidence is often selected to support the pre-existing belief, known as rationalization, cherry-picking, or confirmation bias. And rational certainty is almost never complete. A scientist would never say they are 100% certain of any scientific conclusion, regardless of the amount or quality of evidence. Scientists and other scholars can live with uncertainty as long as they know how uncertain. They factor in tolerances, margins of error, and so on to strictly define the extent of any uncertainty. Absolute certainty should be mistrusted as it can close our minds and take away our objectivity. But how certain can we be of this? What do you think?
We will now examine various perspectives from empirical arguments of John Stuart Mill to analytic views of David Hume and the synthetic a priori reasoning of Immanuel Kant. First perspective is the empirical view. The empirical argument. The British philosopher John Stuart Mill of 1808 to 1873 was an English philosopher and economist. He was prominent as a publicist in the reforming age of the 19th century and remains of lasting interest as a logician and an ethical theorist. He claimed that our certainty in mathematics arises from a vast number of empirical observations, the correspondence theory. The correspondence theory in its simplest form say that truth is a connection to reality. In other words, we can feel certain that 2 plus 2 equals 4 because every other time a human has carried out this calculation, it appears to be true, although math itself is a deductive in nature. Notice that this is an inductive in conclusion. Limitation of empiricism. However, this empirical view fails to fully account for mathematical proofs that go beyond prior experience. The ability to prove theorems without empirical validation suggests that mathematics transcends mere observation. Next, if you conclude that math is not empirical, you might think it's being analytic. That is something that's true by definition, independent of experience. This view is often attributed to Scottish philosopher David Hume, 1711 to 1776. This suggests that math is truth that simply exists out there. Any mathematical operation is therefore simply unpacking the truth. However, there is an ongoing unresolved debate between philosophers over whether math is discovered or invented. Did even numbers exist before someone came up with a definition of an even number? The analytic states that a conjecture must be true or false by definition. However, it seems that nature will never allow us to determine the truth or falseness of every conjecture. Lastly, the synthetic a priori, Kant's revolutionary idea. If we decide that math is neither empirical or analytic, we might conclude that it is therefore synthetic a priori, the knowledge that is found to be true through observation yet exists independently of experience. This view is attributed to German philosopher Immanuel Kant, 1724 to 1804, but it's not really different to the viewpoint of Euclid. Kant argued that mathematical knowledge relies on intuitions of space and time, which are fundamental to human cognition. This view explains how we can have certain knowledge of mathematical truths without direct empirical evidence. Now, we go to the different philosophical implications. We have Platonism, formalism, logicism. First is the Platonism. Many mathematicians and philosophers adhere to Platonism, believing that mathematical truths exist in an abstract ideal realm. This view posits that mathematical objects and relationships are discovered rather than invented, existing independently of human thought. Next is the formalism. Formalists argue that mathematics is fundamentally about manipulating symbols according to specified rules. In this view, mathematical truth is more about consistency with a formal system than about correspondence to an external reality. Lastly is the logicism. Logists attempt to reduce all the mathematics to logical principle. This approach seeks to ground mathematical certainty in the fundamental laws of logic, providing a unified foundation of mathematical knowledge.
Platonism, rendered as a proper noun, is the philosophy of Plato or the name of other philosophical systems considered closely derived from it. In narrower usage, Platonism, rendered as a common noun, refers to the philosophy that affirms the existence of abstract objects, which are asserted to exist in a third realm, distinct both from the sensible external world and from the internal world of consciousness, and is the opposite of nominalism. Lower-case Platonists need not accept any of the doctrines of Plato. In a narrower sense, the term might indicate the doctrine of Platonic realism. The central concept of Platonism, a distinction essential to the theory of forms, is the distinction between the reality which is perceptible but unintelligible, and the reality which is imperceptible but intelligible. The forms are typically described in dialogues such as the Phaedo, Symposium and Republic as transcendent perfect archetypes of which objects in the everyday world are imperfect copies. In the Republic, the highest form is identified as the form of the good, the source of all other forms, which could be known by reason. In the Sophist, a later work, the forms being, sameness and difference are listed among the primordial great kinds. In the 3rd century BC, Arcesilaus adopted skepticism, which became a central tenet of the school until 90 BC when Antiochus added Stoic elements, rejected skepticism, and began a period known as Middle Platonism. In the 3rd century AD, Plotinus added mystical elements, establishing Neoplatonism, in which the summit of existence was the One or the Good, the source of all things. In virtue and meditation, the soul had the power to elevate itself to attain union with the One. Platonism had a profound effect on Western thought, and many Platonic notions were adopted by the Christian Church, which understood Plato's forms as God's thoughts, while Neoplatonism became a major influence on Christian mysticism, in the West through St. Augustine, doctor of the Catholic Church, whose Christian writings were heavily influenced by Plotinus Aeneas, and in turn were foundations for the whole of Western Christian thought.
Formalism is a theory that holds that statements of mathematics and logic can be considered to be statements about the consequences of certain string manipulation rules. For example, Euclidean geometry can be considered a game in whose play consists in moving around certain strings of symbols called axioms according to a set of rules, called rules of inference, to generate new strings. In playing this game, one can prove that the Pythagorean theorem is valid because the string representing the Pythagorean theorem can be constructed using only the stated rules. According to formalism, the truths expressed in logic and mathematics are not about numbers, sets, or triangles or any other contensive subject matter. In fact, they aren't about anything at all.
They are syntactic forms whose shapes and locations have no meaning unless they are given an interpretation. Formalism is associated with rigorous method. In common use, a formalism means the outturn of the effort towards formalization of a given limited area. In other words, matters can be formally discussed once captured in a formal system, or commonly enough within something formalizable with claims to be one. Complete formalization is in the domain of computer science. Formalism stresses axiomatic proofs using theorems, specifically associated with David Hilbert. A formalist is an individual who belongs to the school of formalism, which is a certain mathematical philosophical doctrine, one of the schools of thought in the philosophy of mathematics, putting forth the theory that mathematics is an extension of logic and therefore some or all mathematics is reducible to logic. Bertrand Russell and Alfred North Whitehead championed this theory, created by mathematicians Richard Dedekind and Gottlob Frege. Dedekind's path to logicism had a turning point when he was able to reduce the theory of real numbers to the rational number system by means of set theory. This and related ideas convinced him that arithmetic, algebra and analysis were reducible to the natural numbers plus a logic of sets. Furthermore, by 1872 he had concluded that the naturals themselves were reducible to sets and mappings. It is likely that other logicists, most importantly Frege, were also guided by the new theories of the real numbers published in the year 1872. This started a period of expansion of logicism, with Dedekind and Frege as its main exponents, which however was brought to a deep crisis with the discovery of the classical paradoxes of set theory. Frege gave up on the project after Russell recognized and communicated his paradox, exposing an inconsistency in naive set theory. On the other hand, Russell wrote the Principles of Mathematics in 1903 using the paradox and developments of Giuseppe Peano's school of geometry. Since he treated the subject of primitive notions in geometry and set theory, this text is a watershed in the development of logicism. Evidence of the assertion of logicism was collected by Russell and Whitehead in the Principia Mathematica. Today, the bulk of modern mathematics is believed to be reducible to a logical foundation using the axioms of Zermelo-Fraenkel set theory, which has no known inconsistencies. Thus, to some extent, Dedekind's project was proved viable, but in the process the theory of sets and mappings came to be regarded as transcending pure logic.
These points provide a broad view of how infallibility and certainty are conceptualized in mathematics, and how, despite its rigor, mathematics has intrinsic limitations when viewed from a broader philosophical and logical perspective. So that's the end of our discussion, and thank